Hi students, welcome back to Kirsty's virtual classroom. Today we are talking about mass extinctions. All right, so what is a mass extinction? So every once in a while, life on Earth experiences some sort of die out of a concentration of species. And for something to be considered a mass extinction, we need to lose 50% or more of those species. And so we'll see large groups, like you're probably familiar with the dinosaur extinction. Large groups die out, and then another group will typically take over in the next time period. And so we'll talk about a few of these extinctions that are more than 50%, and then we will also talk about a few that are less than 50% that were not considered mass extinctions, but they were still extinctions. So how do we know these extinctions exist? So obviously, paleontologists are looking at fossils on a very regular basis, and every time there's construction, a paleontologist has to come in and clear a site. So those sites are construction-based sites. And there's also other ways that we find out about fossils just from research discovery. And we have one in Madeira that was found from a landfill. They were, burying trash in Madeira County and came across fossils. So paleontologists had to step in, exhume all of those fossils, and then start recording their information. And so by looking at all of these fossils on Earth and getting a lot of data from these fossil discoveries, where they are, what type of rock they're in, how old they are, all of that stuff helps us understand when these species lived, when they suddenly disappear, and what happened in the future. And so if these species suddenly disappear from the rock record, that's considered an extinction event. And so throughout Earth's history, there have been 5 major extinction events. We call them the Big Five. And this graphic kind of shows you where those lie on the geologic timescale. The most recent event being the Cretaceous-Tertiary boundary. And this one also talks about the 6th event that I will talk about at the end of this presentation. That is what basically humans are contributing to mass extinctions. So we do have a few on here you may have heard of before, and a couple you may not have. So we'll go through these 5 individually: the Ordovician-Silurian, the late Devonian, Permian-Triassic, the end of the Triassic, and then the Cretaceous-Tertiary boundary that everybody's most familiar with. All right, so with the Ordovician-Silurian extinction, there was not a lot of land animals here at the time. Most of the animals were in marine environments. And so this included things like mollusks, trilobites, graptolites, brachiopods, chondons, corals, etc. And all of these went extinct 443 million years ago. They were all key members of the Paleozoic fauna. And here we saw 52% of the species that are documented by paleontologists never show up again in the rock record. And so this is a pretty significant die-off. This was one of the first mass extinctions. We do have an extinction event prior to this that was not as drastic. We only lost about 15% there, but this was the first mass extinction we saw in Earth's history. This was first defined by Charles Lapworth. He found a stratigraphic column in Scotland that really gave him a good indication that these organisms had died out at the end of the Ordovician, the beginning of the Silurian. And then after this extinction event, it took Earth about 50 million years to recover to the diversity level that it was prior to this extinction. So what probably caused this extinction? Most likely global cooling. And so what was happening around the Ordovician was that a supercontinent named Gondwana was isolating itself around the South Pole. And what we know about the South Pole is that it's very cold. It's cold because the incoming solar rays hit it at a very low angle, and so the concentration of that solar ray is over a larger area, so it makes it really cold there. And so what ended up happening is we saw a really drastic drop in seawater temperatures, about 5 degrees Celsius, during the latest portion of the Ordovician. And then we also see lots of evidence of glaciation during this time, which correlates well with the South Pole. And that kind of gives us a good indication that the globe was cooling. In addition to the glaciation, glaciers need water, right, to form. So what that does to sea level is it drops it. So with dropping sea levels and global cooling, you're going to disrupt a lot of the life on Earth, right? It's not going to be able to adapt quick enough to that change in temperature and then loss of actual volume of water. All right, so a couple things that drive global cooling. I've already talked about Gondwanaland being over the South Pole. That would have drifted there from plate tectonics. So we know that the plates are moving on Earth from convective cells in the mantle. And as that happens, it pushes and pulls continents apart and together. And then we also saw a lowering of greenhouse gas levels through some changes in the climate. And so the kind of diving more into that, what that means is this can be done from a tectonic perspective and from a reduced sunlight perspective. So with greenhouse gases, we're familiar with them more from a human impact perspective, but they do fluctuate from natural things happening on Earth. So for example, during a mountain building event, you might see a lot of volcanic activity, and volcanism causes a lot of CO2 gas to go into the atmosphere, and that CO2 gas will produce more greenhouse gases into the environment, blocking sunlight, contributing to a change in environment. So it's really what's happening in a lot of these extinctions is there is a change in environment. A couple of them are attributed to meteorite impacts, but there's also a component of change of environment. So it's global cooling, global heating. We have a change in concentration of CO2 or oxygen in the atmosphere, and that causes things to die. There is some limestone in Sweden that show a lot of meteorites very close to the Ordovician time. So there might also be, and there's a picture of one here, it's a meteorite within a limestone. That might also be an indicator that there were some meteorite impacts that also reduced sunlight, because as meteorites impact Earth, they kick up a bunch of dust. That dust gets suspended in air and it blocks incoming solar rays. All right, moving on to the late Devonian extinction. The Devonian was primarily dominated by fish. So this was considered the age of fish, where we saw a lot of diversity among that species develop. And so we saw sharks, we saw the first finned fish, ray-finned fish, lobe-finned fishes, jawless fishes. So lots of diversity there. And the extinction was kind of prolonged. So that's why it's called late Devonian instead of a transition between two time periods. It took about 20 to 25 million years for the extinction to actually occur. And most of that die-off happened between 74 million years and 359 million years. So it's a pretty large range there. That's that 20 million year range. 99% of reefs were destroyed, which is significant. The diversity in fish was cut back significantly. And then a lot of these marine groups were severely brought back or eliminated altogether. And so we see corals that were also taken back about 40%. And then some of our brachiopods were completely extinguished. So a pretty significant drop there in concentration of some of these life forms. All right, so one of the things in this extinction event that is important is looking at black shales. So black shale is, just as you would imagine, it's a shale that is really dark in color, or technically lacking in color, right? So we have muddy sediment that's going to form under low oxygen or anionic conditions. Organic carbon will be entered into the sedimentary record. It's wrong word there, sorry. Giving its host rock that dark color. So when there's a lack of oxygen in the environment, rocks will take on a darker color, and hence the black shale. So here we had Earth's land surfaces saw a growth in the first forests. And what's happening is these trees are consuming CO2 and releasing oxygen. And so when all of those byproducts go into the oceans eventually, there's all these extra nutrients that can drive up the production of algae. And when algae dies, it rots, and those dead algae cells consume all of the available oxygen in the water, creating what we call dead zones. And those dead zones are areas where there's a lack of dissolved oxygen, and if a fish happens to swim through that dead zone, it can asphyxiate. So it does need oxygen in the environment, dissolved oxygen within the water, in order to survive. With the lack of that, fish would start dying. So with huge deposits of black shale, this became really evident that this was one of the major problems, was the oxygen concentration in oceans. We also saw some removal of organic carbon from the biosphere, which means that the atmosphere will be relatively depleted in CO2, which is a greenhouse gas that helps warm the climate. So that means that it's going to drop global temperatures again, and obviously drop in global temperatures, increase in global ice during the late Devonian is going to also kill some things off, right? So things get used to a certain temperature, and if there's a huge change in global temperatures, then they are going to struggle to survive. All right, so here we have a lack of oxygen, and we also have, again, some global cooling occurring. All right, moving on to the Permian-Triassic extinction. This happened about 252 million years ago. This is one of the more popular ones, other than the extinction of the dinosaurs. It's also referred to as the Great Dying because there were 62% of marine genre going extinct, as well as severe impacts among the terrestrial life. It's estimated that only about 17% of all species survived. So that is significant. And it is the closest our biosphere has come to being deleted, so completely wiped out, no life on Earth left. It's the only mass extinction of insects as well. So pretty significant amount. So most likely, the Great Dying was caused from volcanoes. So what happened here is we had some global warming from excess CO2. Remember I said volcanoes expel CO2 gases into the atmosphere, and when that occurs, it not only blocks sunlight, but it also causes a change in global temperature. It creates kind of like this insulated little blanket. And so we have 5 to 10 degree increase in global temperatures during this time. The volcanoes that erupted were in China, which is the Emishan traps, and then there's the Siberian traps. The Siberian traps are estimated to have produced 1.5 million cubic kilometers of lava that erupted about 2 million square kilometers in an area. That is huge eruption. So the CO2 rates at the end of the Permian were predicted to be about 8,000 parts per million. So ppm is parts per million. Today, they're 425 parts per million. And people talk about how bad our CO2 rates are today. That is an astronomically higher number, right? So obviously that is going to cause devastating events. And then in the ocean, there was also underwater volcanoes also releasing some of that gas, leading to periods of too much oxygen or too little oxygen. So during the Great Dying, there was 70% of land species that went extinct, and 95% of the marine species went extinct. And it took 30 million years for life on Earth to recover. So pretty significant impact to life on Earth. All right, moving on to the Triassic-Jurassic extinction, which is right before the dinosaurs. So during the Triassic, theropsids, there's the word, flourished, and they were found when the dinosaurs were around a little bit, but they were not the main event. The main event were these crocodilian-like animals, which there's a picture of a couple of them at the bottom of the screen there. And during this time, the these critters were kind of taking off, and dinosaurs were around a little bit. And then by the time the end of the Triassic occurred, we saw these crocodilian-like animals die off, and dinosaurs took over until their inevitable extinction. So this happened around 252 to 200 million years ago, and we lost 76% of marine and terrestrial species. So that was pretty significant. The only thing that really survived were dinosaurs and trees, which is fairly interesting. Most of this is attributed to very similar issues: large volcanic eruptions, CO2 level spike, and global warming. Okay, so all of those things you can see are common themes as to what's causing mass extinctions. A lot of them are very similar. We do see around this time, the breakup of Pangaea, which was our largest supercontinent. And during that time, we saw some volcanism in what we now call the Central Atlantic Magmatic Province, or CAMP. It produced basalt and gabbro in volumes of 2 to 3 million cubic kilometers. It's a lot of lava. It's a lot of material. So the CO2 level was predicted to be about 7 to 8 times as high as it is today, which will cause a 3 to 4 degree spike in global temperatures. Obviously, not good for anybody. All right, and then we get to the famous Cretaceous-Tertiary extinction, which caused the extinction of the dinosaurs. Here we lost 76% of all species on Earth. All dinosaurs are wiped out, and this is often referred to as the KT boundary. So I'll refer to that back a couple times. During the Cretaceous, dinosaurs were the dominant species, and they lived for some 165 million years. In the seas, we had a lot of oysters. So if you've ever seen that spiral fossil that everybody loves, they sell earrings with them. They sell pendants, all kinds of things. Those are ammonites. Those are also very dominant in the Cretaceous as well. And the Cretaceous wasn't really somewhere you wanted to be. It was really hot. There is absolutely no glacial evidence found anywhere on Earth during this time period. So as you can imagine, that means that the planet is really hot during this time. I mean, we have glaciers today and we consider today hot. So kind of could put you in perspective there. That's why you see a lot of like tropical leaves and stuff when they have artist renditions like this one with dinosaurs in them from that time period. And again, we have more volcanic eruptions, which is why you also see artist renditions of volcanic eruptions with the dinosaurs. This one was in India, and it produced 1 million cubic kilometers of basalt, which covered about 500,000 square kilometers. This took place over about 30,000 years, and it was originally thought to be the primary cause of the extinction, but it might have been just a contributing factor, because in 1980, a couple of geologists and a physicist who happened to be father and son, Walter Alvarez and Luis Alvarez, produced a publication that said that no, they died from a meteorite impact. And so what they were looking at was a 4 centimeter, which is pretty small, layer of clay that had iridium in it. And a large concentration of iridium had to be fallout from a single meteorite impact somewhere on Earth. And there wasn't a lot of evidence of this impact yet until a few years later when they found spherules and shocked quartz near the KT boundary, so rocks that were around that boundary. And spherules are little glass droplets that form when rock melted instantaneously by tremendous heat and impact, is flung into the air as billions of tiny droplets. So there we have evidence of impact. And then shocked quartz is very similar, but it's a little bit different. It starts off as a solid crystal that is formed as quartz, but then it deforms as it's impacted or shocked, and it wrecks some of the crystal lattice. And there's an image of it right there, kind of showing you that those lines indicate that we're looking at some shocked quartz. And then a couple years later, we found the Chicxulub crater, which is in the Yucatan Peninsula, so pretty close to where we are, is where the presumed impact crater for this meteorite impact that destroyed all of the dinosaurs was found. It's about 10,000 square miles in its area, and it has ages, limestone with ages up to 66 million years, which indicates that the last 66 million years has been filling with limestone. So around 66 million years ago, which is when the dinosaurs went extinct, it was created. So the discovery of the Chicxulub crater was a very important discovery in providing evidence for the impact. And then post the Cretaceous-Tertiary boundary, we saw the development of mammals. So the age of mammals began after the dinosaurs died off. Mammals were able to thrive, which led to, obviously, us. And the only living dinosaurs on Earth right now are birds. Birds are technically a relative to dinosaurs. All right, moving on to other mass extinctions, but they're in quotes because they're not as impactful. We didn't see more than 50% of life disappear. So we have the Great Oxidation Event, the Cambrian Explosion, the Eocene-Oligocene Transition, the Pleistocene Megafauna Extinction, modern biodiversity crisis, and the last life on Earth, which is going to be those last two are future extinctions. All right, so the Great Oxidation Event is one of the earliest extinction events recorded in Earth's history. This took place around 2 to 2.5 billion years ago. It was a very drawn-out event, and it lasted some 400 million years. That's a really long time for an extinction event. We didn't lose that much life. I think I think it's like 15% of life was erased from Earth. The interesting thing here is that most of Earth's surface was covered in water at this time, and so there was very little life. They were very simple-celled organisms and not necessarily considered animals quite yet. And so we have things like the banded iron formation, which there's a photograph there of the banded iron formation, which is a very good indicator of this great oxidation event because in early Earth's oceans, there is a high concentration of iron. That high concentration of iron is found in the banded iron formation. Anything younger than the banded iron formation starts to lose that iron concentration, and we see more oxygen-based sediments. And so we see what we call red beds, which are terrestrial sediments. And so from then you can see that free oxygen was starting to develop. Early oceans did not have this free oxygen, and with that, you can only develop a certain type of organism. With the free oxygen, that's where, as you probably remember from a couple minutes ago, we were talking about mass extinctions, where lack of oxygen was a problem for a lot of species. And so here it's kind of the opposite. With extra free oxygen in the oceans and in the environment, we saw a loss of some of these bacteria and microbes, and they just could not handle that much free oxygen in the environment, so hence they died off. So this is the Great Oxidation Event, where oxygen started to be more present in our oceans and atmospheres. And then we have the Cambrian Explosion. So this happened in the Cambrian, from the Ediacaran to the Cambrian. And the Cambrian was where a bunch of animals blossomed and they had hard parts. So shells and other hard parts are really good for preserving a fossil. And the Ediacarans were not hard-bodied, so they were very soft-bodied, and a lot of them were kind of embedded into the ocean floor. And so they didn't have a lot of things to kind of defend themselves, right? They were very soft-celled, on the bottom of the ocean floor organisms. And these could be like some jellyfish and some sea pins. So then when the Cambrian organisms showed up, they were able to go further up into the water column and they blossomed a lot more at the base. And because they had hard body shells, they kind of took over the environment or the ecosystem that the Ediacaran organisms were in. And so they didn't have a way to defend themselves. And most of them died out. All right, moving into the Eocene-Oligocene transition. So halfway through the Cenozoic, Earth's climate shifted again to a cooler state. And this happened when Antarctica broke up from Australia and South America and kind of took off towards the South Pole. There was obviously a temperature decrease in the global sea temperature, about 4 to 5 degrees. And by about 30 million years ago, there were new glaciers growing in the southern continent, which also changed the climate, right? Here we saw 15% of species to be extinct from that temperature difference. And some of the impacts and where we see those impacts are listed there with some ages. So they all kind of correlate to around that 30 to 35 million years. All right, and then the Pleistocene megafauna, the poor large mammals that took over after the dinosaurs that then went extinct, maybe because of humans. So this is the most recent extinction in Earth's history. It skipped sea life, it skipped plant life, it skipped small animals and nocturnal animals, and it focused primarily on birds and the large mammals like the saber-tooth and the mammoths and mastodons, the giant short-faced bear, the ground sloth. All of those went extinct during the Pleistocene. There are a lot of different theories. There's no real clear indicator what caused a very specific extinction of specific animals during this time, but some of them include meteorite impact, a change in the ice age. So these were all ice age mammals, but a shift in that ice age during that time, and then human overhunting. So I think it's probably, as with a lot of these extinctions, a combination of all of these things leading up to it, because humans at the time, I don't think had the technology to completely wipe out all of these mammals. Like, that's absurd. Obviously, it contributed to it because as we got more skilled in hunting during the Pleistocene, we were definitely able to hunt and kill these animals for food, obviously. And a mammoth, if you killed a mammoth, would probably feed your family or your village for a month, right? That would be a significant amount of meat for you, but you wouldn't need to kill 50 of them, right? So I think that one might be a little exaggerated. I think today we are more likely contributing to overhunting than maybe in the early Pleistocene. All right, and then now we have a modern biodiversity crisis. Most of you are familiar with this, but this is dubbed the 6th Great Extinction. So we may be causing the next great extinction. Yay. This is primarily caused from habitat destruction, fragmentation, invasive species, disease, pollution, climate change, all of the bad things that humans bring to the earth, right? So unfortunately, the rate of extinction that seems to be happening among a lot of species that are on Earth today is a lot higher than any of the other 5 big mass extinctions that I've talked about already. This is happening in the matter of centuries instead of millions of years like the other mass extinctions I talked about. So this is really unfortunate. Hopefully in the future we are better at this and we are helping to preserve habitats instead of destroy them. All right, the last life on Earth. This is our estimated doomsday. It's estimated around 1.45 billion years in the future, which, lucky for you, you won't be around unless there's some great technology that happens in your future that aids you in being here for longer. But our planet is currently cooling. So since its inception, it's been cooling. And the cooler it gets, the less likely we're going to have anything molten below us. If there's nothing molten below us, there's nothing that's going to drive plate tectonics. If there's no plate tectonics and our core is completely solid all through, we're a completely solid planet, we are going to lose our magnetic field, which helps protect us from solar incoming rays, and it helps keep our atmosphere in place. And so if all of those things go away, we are going to be very exposed like Mars is, right? Mars is an inhabitable surface because you don't really have a good atmosphere. They have a lot of incoming solar rays, solar winds. And so there's not much, and meteorite impacts, there's not much protection there. We don't want that. So in the future, that looks like where we're going. And then about 5 billion years from now, we might be in contact with the sun's surface, because our sun is a G-type star and it is continuously growing as it burns hydrogen. And so eventually it will consume Mercury and it will consume Venus, and then it'll be right at the edge of Earth's surface, and it'll be too hot to live here if the sun doesn't fully consume Earth. So that is the next predicted, outside of our 6th extinction, the final extinction of all life on Earth is maybe about 1 to 2 billion years from now. All right, to summarize all of these extinction events, there is a column on the left that has the name of the extinction event, all of the ones we talked about, the date, the percent extinct. I love the great oxygenation event, where it just goes, I don't know what percentage, and then what the potential cause of that extinction event. You'll see a lot of repetitive information. I talked about all of those already. And with that, I will see you guys in the next video. Bye.